Instead of taking a modal approach with the monomodal basis, what if we were to take a nodal approach using a Lagrange basis? You probably have seen a Lagrange basis used before in any of your previous numerical classes used for Lagrange interpolation. Recall that the Lagrange basis is 0 at all the interpolation nodes except for the basis node, which it's 1 at. In other words, if we were to look at a particular set of, and let's say this is from -1 to 1, we had a set of particular nodes for our interpolation. A particular basis for, let's say, this node would be 1 there and 0 everywhere else, or everywhere at the other interpolation nodes. So it has the general form of the following, where we essentially have a product of a series of terms excluding the point that our interpolation is based on. So we have a compact way that we can actually represent this in MATLAB, and this is essentially just performing these computations. This routine here creates a set of vectors where we're absent the entries in this second vector. So in other words, this is the numbers 1 to n, and then in each of these row vectors we're absent an increasing number. So we could imagine for this first one we're going to have 2, 3, 4, then 1, 3, 4, then 1, 2, 3, etc. So this is defining this behavior here where we're eliminating the node for the particular basis. So each one of these is our set of basis points. And so this is tied to a set of nodes here, which is an array. And then we're using BSX-Fun to be able to perform a singleton expansion along the dimensions so that we can get a fully vectorized expression. So we can pass in a vector of desired interpolation points, and we can pass in a vector of any of the potential Lagrange bases up to big N that we're interested in.